The University of Oklahoma presents Ralph. Ralph's overall design is centered around simplicity and cost efficiency. It was found that in order to most practically achieve the maximum score for the 2021 DBF competition, the design needed to revolve around Mission 2. Ralph features a large fuselage, designed to efficiently carry many relatively small payloads. The reeling mechanism included a continuous rotation servo attached to a custom 3D printed reel. This spools the tri-weave signal wire that tows the sensor. Ralph's overall structure mainly consisted of foam board, minimizing manufacturing time and material costs.
Ralph is designed to be a cargo plane with a span that is limited to just under 5 feet and a total fuselage length of 6 feet. The internal volume for the payload is a 10-inch by 10-inch square that runs for just over 4 feet, allowing for Ralph to comfortably carry a total of 36 sensors. The payload is easily secured by inserting the containers through a door on top of the fuselage, allowing for rapid loading times. Ralph's weight changes depending on the mission being performed, with Mission 1 consisting of completing 3 laps with an empty plane, Mission 2 being the flight with a full payload, and Mission 3 being the sensor deployment and recovery challenge. Throughout all missions, Ralph must take off within 100 feet, and at its heaviest, he weighs just under 20 pounds.
The aircraft aerodynamics were designed to maintain stability while staying within the design limitations of the competition. The 5-foot wingspan limit resulted in a low aspect ratio, highly cambered main wing in order to produce the lift necessary during the heaviest Mission 2 configuration.
The control surfaces on board the aircraft include ailerons, elevators, and a rudder. The dimensions of the control surfaces are shown here. Dimensions were originally derived using approximations from the textbook Aircraft Design, a Conceptual Approach by Raymer, which gave ratios for each control surface with respect to the wing and tail. After initial test flights, the elevator was redesigned from 2 surfaces to 1 continuous surface in order to limit servo count. This reduces the weight and the chance for malfunction.
Ralph was equipped with one Hacker A60 motor and an 18-inch propeller. A dual prop system was considered during the design process, but the interaction between the downwash of each propeller complicated the aerodynamic analysis. Once it was confirmed that a single motor could achieve takeoff in under 100 feet, even with the full Mission 2 payload, the single motor configuration was selected for simplicity of analysis and construction. The propulsion system uses 5 batteries in total, as shown by the table in the bottom right and the diagrams in the bottom left. 2 main propulsion batteries, each with a 100-amp fuse, provide power to the motor through an electronic speed controller. A third battery powers the main receiver and the servos for each control surface. The fourth battery in Ralph's fuselage is used to power a secondary receiver using another electronic speed controller with a battery eliminator circuit. This receiver controls the sensor deployment and recovery system, as well as the Arduino Nano that provides signal to the sensor LEDs. Finally, the LEDs themselves are powered by a 5th battery stored inside the sensor.
When determining trade studies to conduct, it was evident that the highest score would result from the best combination of sensor size and weight for Mission 3 and the number of sensors carried in Mission 2. The plot shown is the result of a trade study of the number of sensors versus sensor weight conducted with an optimization code. It is clear that the highest score results from choosing to maximize either sensor weight or number of sensors. Originally, maximizing the sensor size and weight was chosen, but after rule clarifications made in December, the final design maximizes the number of sensors carried in Mission 2.
Ralph's mission performance is primarily predicted through a MATLAB simulation that takes into account Ralph's propulsion system, drag model, and weight for each mission. In Mission 1, Ralph is predicted to take off in just 16 feet and complete 3 laps in 95 seconds, flying at 80 feet per second. In Mission 2, Ralph takes off in 46 feet and flies even faster at a speed of 100 feet per second, completing the mission in 84 seconds with a payload of 36 sensors. Finally, Ralph achieves a 20-foot takeoff in Mission 3 and flies 19 laps in 596 seconds while towing a 0.14-pound, 4-inch long sensor.